Let's take a look at the velocity addition when you get into relativity. So first, let's do a Galilean relativity example here. So if you have a car traveling along, traveling to some velocity, v sub ce. So this is the velocity of the car with respect to the Earth. And so 50 miles per hour east. Now you're in the back of the car and you throw a ball forward. So this would be the velocity of the ball with respect to the car. How fast is the ball going with respect to the Earth? Well, the velocity of the ball with respect to the Earth would be the velocity of the ball with respect to the car plus the velocity of the car with respect to the Earth. Generally, when you're adding vectors, as long as those are the same, you have a legitimate vector addition equation right there. And so all this works well and good. So if the velocity of the car with respect to the Earth is 50 miles per hour, and the velocity of the ball with respect to the car is 20 miles per hour, then the velocity of the ball with respect to the Earth would be 70 miles per hour. So if you had someone with a speed gun over here who could actually measure the speed of the ball, it would go at 70 miles per hour. However, if you're in a rocket ship and you are traveling, the speed of the rocket ship with respect to the Earth is 0.9 times the speed of light, and you throw something forward, so here's the Earth, and you throw a ball forward at 0.8 times the speed of light, well, the velocity, if the Galilean relativity were true, the velocity of the ball with respect to the rocket plus the velocity of the rocket with respect to Earth would give you the velocity of the ball with respect to Earth. So 0.9c plus 0.8c is 1.7 times the speed of light, which is not going to happen. This is Galilean relativity, so we have to somehow account for the relativistic aspects of it. And so now let's get into some of the beautiful math involved here. So we'll go back to I have my S frame here, and I have a particle here that's moving at some speed v. So this is the speed of the particle, some velocity p, v, velocity of the particle with respect to s, and that is, we'll just let equal to v. And that's going to be equal to the distance over time. I'm dropping the deltas for simplicity of writing. I have a different frame here, S prime frame, that's looking at this, and it says, so the velocity of the particle with respect to S prime, we're going to say is W, and that's equal to X prime over T prime, because there are different reference frames. And S prime frame is moving at some speed u, and so the velocity of S prime with respect to S is u. So I know that W is X prime over T prime. That's equal to gamma X minus ut over gamma T minus u over c squared x, using the Lorentz transformations. The gammas are going to cancel out, and what I'm left with is x minus ut over t minus ux over c squared. Not particularly simplified quite yet. I'm going to multiply top and bottom by 1 over t, because I know where I'm heading. And so I get x over t minus u over 1 minus u over c squared times x over t. X over t, we established that is the speed of the particle in the S frame. So that's going to be equal to v minus u over 1 minus, and we have x over t again, u v over c squared. So this is the speed of the particle from the S primes frame. Now if we wanted to go in the other direction, what is the speed, what is v in terms of w and u? Well, we're sort of basically going in the other direction, and we'll do sort of a hand wave here, but we end up with v is equal to w plus u over 1 plus u w over c squared. Now from a solving point of view, these signs are the same. And also from a solving point of view, Galilean relativity is just the denominator is equal to 1, because u and v are both so small relative to c. So Galilean approximation, we end up with W is equal to V minus U, and here we'd end up with V equals W plus U. Not a huge shock because if I add U to both sides. So when you're solving one of these problems, you need to figure out what is it in Galilean relativity, and then you can solve it with the special relativity. So if we go back to our problem of I have Earth, I have rocket. Rocket's going at 0.8. Oops, wrong problem. Rocket's going at 0.9 times the speed of light, and then I have a ball inside going at 0.8 times the speed of light. We figured out that the speed from the Earth's point of view was going to be, in Galilean relativity, 0.9c plus 0.8c. That is what we did before. But now we divide by 1 plus, same sign, and then the product of the two vectors over c squared. And so we end up with 1.7c on top, and on the bottom, 1 plus 0.72. So I have 1.7, 1.72, divide by that, and I end up with 0.988 times the speed of light. That is how fast the ball would be going relative to the Earth. And that's how you work the relativistic velocity problems and the velocity addition problems.